Hi, my name is Bob Grinier and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me here this 17th of July 2022, where we will be discussing the from under 2 times to 10 times excess heat, leveraging the power of exotic vacuum objects. So I may have a Zoom call after this if people want to discuss things like where have I been for the last couple of weeks and what's the plan for moving ahead. I will post a link in the current remote view blog when I finish this presentation. This is not going to be a long one, but I've missed you guys, and it's good to be back with you. This is a little bit scrappy, but because ICCF 24 is coming up next week, I think this is the right time to get this out there and to make it short, because I believe this is a key approach that will deliver a significant thermal gain for those that are seeking to produce heat-producing reactors with exotic vacuum objects. You will see for the first time reasons why I chose certain things in the past, and it's came from an understanding I had, and you'll see the kind of histrionics behind it, and it then led to me questioning someone, or rather having a conversation with someone a number of years ago, and they were kind of forced or backed into a corner to reveal something to me, but because it was their own IP and whatever, it wasn't public knowledge. I kind of hoped that it would be made published, and I saw this person's presentations for year after year after year, and it wasn't made public. And so I made a comment about this in ICCF 22 during my presentation about Alexander Parkhomov's work. But in the most recent presentation of this author, he kind of let it slip a little bit, and in my questioning to him, I encouraged him, let's say, to make the knowledge public without specifically giving an indication as to the implications. But of course, the implications I already knew, so I feel comfortable with getting this out there. And we're in a situation right now where we need to deliver and move forward with producing heat and light and electricity producing systems, and this is a key component, I believe, to delivering that. Okay, so hi Thor, hi Lucas, hi Rare Condition, hi Artifact, Cosmic Dave, David Bidlier, we have D2 105K and Ken Pratt. So great to have you in the room. So I'm just going to tweak one slide here because I need to put something on the end of the presentation so that I don't forget. We can move forward. Okay, all right, I'll put that in there and I can talk to that later. Okay, so we are talking about from under 2 times to 10 times excess heat. Now, I don't know if you recall, but way back when we were doing when we were doing replications of Francesco Celani, our first replication we saw 12.5%. That was back on an experiment that started at 12 seconds past 12 minutes past 12 of the 12th of the 12th of the 12th California time. I thought that would be a good date to start it and time to start it, because it's not going to happen again for a very long time. And so basically we started then, and 2 days later we saw this excess heat of 12.5%, and we bumped that up, and we managed to achieve a little bit more than that. We never achieved what was claimed at NI Week and at ICCF 17 by Francesco Celani, but it turns out that his actual data was closer to ours when it was adjusted for the incorrect calculated input power using the National Instruments system that was used at the time. And it took us 2 years to come to an agreement with how we could get that out there sensitively. But anyway, That's in the past, and our excess heat came down. His came down to meet, came up, and his excess heat came down, and we kind of met quite closely. Now, Francesco has exceeded that by some margin, I understand, since in various experiments, and in our own experiment with the nickel hydrogen and lithium aluminium hydride, we had some indications of having higher excess than that in our active reactor as compared to our control. But in none of our experiments really did we exceed something more than about well, we were always under 2 times, somewhere between 1 and 2. And the problem with that, it's not useful heat, and also it's heat that still is very easy to challenge. Now, the first reactor that we were exposed to that claimed to get around about a 10 times gain was the Suhas-Ralkar Echo reactor in India in 2017, but we never actually got to do some calorimetry on that. We took all the equipment to do calorimetry, but the story goes that the bank locked him out of his own lab, and then the equipment was moved, and that's all in the past. But we got what we needed from that, which was our first look at strange radiation emissions from an ultrasonically produced fuel. But it is important, the content of that fuel, because it contains certain elements which we're going to discuss tonight as being very relevant for the science here. Okay, so if I go here and we go to the next slide, which is here, and I dump myself down there, I'm going to talk about first this report of the first successful Celani wire replication. And essentially I flew to Rome, and it didn't really concern me or faze me at the time. I really don't know why in hindsight, but I was asked to make this presentation in an army base in the centre of Rome, and you know, I didn't even think about it at all. I just oh, it's going to be there. All right, well, we'll go and do a presentation there. So at the back of the room, we had a laptop and running, and it was showing the live data coming from Mathieu Vallat's lab in southern France, and it was there producing the excess heat based on the calibration that he had done. And the reality of that whole thing was that when we were trying to do the original replication attempt, we had very good contact with Francesco Celani, and he was open to every part of the discussion. However, he said during ICCF 17 that he was going to go to using fused quartz for the enclosure of his reactor. And the reason is that he was noticing that the higher he took the temperature, the more excess heat he was getting. And so therefore, because the borosilicate glass that he was originally using was unable to go above sort of 350 degrees without becoming soft and failing, then he wanted to put in this fused quartz, which of course, as you know, can go up to 1,650 or whatever, and still be intact. So we thought that's what he's going to do in our replication. Let's do what he's going to do next. And Ryan Hunt at Hunt Utilities Group in Minnesota in USA, he tried this first, having sent a clone of the cell that Hunt Utilities had built on behalf of the MFMP to Mathieu Vallat. And when he ran it, it was absolutely zero excess. And so we thought, well, okay, we've done the first replication, we've done the cardinal sin in this field of trying to improve the actual experiment that we're trying to replicate. So Matthew found a glass blower who produced the borosilicate glass tubes, and that became the experiment that we ran on 12 seconds past 12 minutes past 12 on the 12th of the 12th of the 12th, which produced this 12.5% excess heat 2 days later. And so that was very, very satisfying. And the interesting thing was, when I had given that presentation, I was walking out of the room, and there was like the presentation room, and there was a hall going out to the outside of the building. And I was just walking out that room, and behind me, this huge medalled general, I think it was, I could hear these steps like briskly running up behind me, and I felt this like tap on my shoulder, this shoulder, but it was this one, this shoulder from behind, and I turned round, and there was this guy just there, and he says, "You need to use an alkaline metal." And I thought, well, this is a bit weird, like racing through my head. And I thought, well, you know, what alkaline metal would I think of first? Well, Pons and Fleischmann were using lithium deuteride in their experiments. So I suggested lithium. And he just kind of gave a slightly approval, wry kind of facial expression. There wasn't a smile, there wasn't a nod, or whatever. You just got the sense that he'd done his job, and he kind of went off. And that was a bit bizarre, because that was the 14th of December 2012, nearly 10 years ago. And so I had in the back of my head lithium, and it turns out that when I was looking at this, that the actual borosilicate glass, of course, contains boron, but it also had, I think, 3.5% or something lithium carbonate there, typically, as a flux. So within the silicon dioxide, you have lithium, boron, and carbon. And for those people that know anything about nuclear technology, the first demonstration of both fusion and subsequent near immediate fission was lithium-7 being hit by a proton going to beryllium-8 and fissioning to helium atoms, and that is an aneutronic fusion. Of course, you have the boron-11 to carbon-12, and then you have clear interactions, it would seem, with carbon, which we'll talk about later. Okay, so this was my starting point way back on December the 14th, 2012. So boron really stuck into my head. And, you know, in 2015, we visited under Project Fedora, Francesco Piantelli on his, in fact, in late 2014 we visited him, but in 2015, January, because of Project Fedora, we visited Piantelli in his lab and his home. He was very gracious in central Italy, and he told us precisely how his reactor, the most famous reactor that he and Focardi had built, and the main core of the inside of that reactor was made of Maycore. Okay, so it had this material which is a machinable ceramic, and when I was thinking about this boron thing, it occurred to me that Maycore might contain boron. I don't know why. I was interested to look at the ingredients, and I found that it has 7% boron trioxide. Okay, so then a little bit later down the line, Parkhomov sent me, I think it was his KV3 reactor, one of his early large producing excess heat producing reactors, and the central tube in that particular reactor was boron nitride. Okay, and you know, that got me thinking about, you know, covalent ionic ceramics and so forth, and in respect of these reactors. But here we have Piantelli with boron, and also boron nitride in Parkhomov's reactor. Then Piantelli came out with his theory that you have these protons ejected, and that you want a secondary material, and he preferentially either had lithium or boron, and he shows in his patent that lithium-6 and lithium-7 goes X, Y, and Z, and the boron-10 and boron-11 with the proton interactions, you get these excess heat, but preferentially it's lithium-7 or boron-11. Okay, preferentially above boron 11, it's lithium 7. So it is in Piantelli's patent. So at the ICCF 21 between the 3rd and 8th of June 2018, I sat down with Francesco Celani and I said, look, we had this experience with your original Celani wire reactor, and I really think that the borosilicate glass was playing a key role in producing the excess heat. And I've seen this thing with Piantelli's Maycore and so forth. So I think, and you know what he says? He says, that would explain it. He said one of his previous reactors that was producing a lot of excess heat had a central support, unlike the ones that we were producing, which had a ceramic tube and it had a piece of mica supporting it, and the mica that he used was lepidolite, and the lepidolite actually has lithium in it. Is the mica, unlike muscovite and so on, it has lithium in it. We were using, I think, muscovite, so we didn't have the lithium in there. But he said that the central support structure of that particular heat-producing reactor was made of Macor, obviously, that has this 7% boron trioxide. And he said, notably, he couldn't understand why the thermocouple that was in the center of this Macor, like in the center of the reactor, was hotter than, you know, any other part of the reactor. Something along those lines he gave me. It was a curiosity to him. Now, if it was producing something that was interacting with the boron in the Macor, then that could actually create heat, and therefore you would have this hot core that would explain what he was doing there. So I'm going to leave that one to the side, and now I want to talk about pseudo-neutrons, and I'm going to show this presentation that came subsequent to my meeting with Francesco Celani, where I discussed this boron hypothesis with him, this boron lithium kind of hypothesis. And this was published on the 4th of July 2018, and you can go and see it at this YouTube address here, if I actually show it to you there. And this is going to be the person who is going to be the subject of most of the rest of this presentation. And this is in, I think, the joint Russian Plasma Physics Institute. And this is a Tesla coil here. And this is an isolated plasma flow reactor of one Anatoly Klimov. And you've got the swirl that comes in here. And this is the intense bright action that occurs where the plasmoid hits the target anode with the material in it. So it's coming out of the cathode, it has a swirl to keep it in line, and so forth. And you can see a range of detectors here and here, and what they were observing is what they call pseudo-neutrons. They're not real neutrons, they're things that behave a little bit like neutrons, but they're pseudo-neutrons, okay? So I will play a bit of this, and you'll see Anatoly in the view there, maybe. So this is Anatoly here on the left. You see all these gas bottles here, and now, if you go and look at this video, it's not necessary to go through it, but you will hear them having this discussion about these neutrons or pseudo-neutrons or fake neutrons. So when you get a chance, I suggest you go and look at that and use the auto-translation on your phone or whatever. Anyway, this is Anatoly Klimov, and this is in Sochi on October the 3rd, 2018. This is when I had the honor of being able to present the first, I guess, I think it was a very large chunk of O-Day slides. It was the first opportunity I had with some ears that I thought would be receptive enough to listen. And this was actually the day before I took this photo when he was giving one of his presentations. And Anatoly has been running the weekly meetings over the period of the sniffle situation. And he's done a fantastic job. But all of this time, and all of the time since October the 3rd, 2018, I've been, well, in fact, it was October the 5th when we had our conversation. I've been wanting him to say something, and he didn't. But anyway, I'm going to tell you how it came about, and we will see. Right, so this is the Hutchison Coral Twist sample, sample 18, I believe it is. And this is on an XRF detector. And on this little experiment that we did here... So what we did here was... I'm going to kill the audio here. Basically, there was a phallico-soliton 2 spots here that I had identified as target for analysis. And when we looked at those... we found that the 2 spots of that had identical elements, which included elements which shouldn't be in there, like this lead and zinc and so on that shouldn't be in there. Okay, and then we looked at the area in between, and in the area in between, it was more like aluminium without the lead, and so forth. So, and without the iron, of course, 227 aluminiums goes to iron 54, and we see this synthesis in other experiments. So the bit in the middle, which is the less damaged Hutchison effect material, didn't have it, and the synthesis of high amounts of iron and also the synthesis of lead, but the bit on each of the two ends of the phallico-soliton did, and they were essentially exactly the same material. So this was put on a octopole mass spectrometer. This is a derivative of the technology that was developed by one Kenneth Radford Shoulders, the quadrupole mass spectrometer, and I took a hacksaw to this end, I believe it is, of the sample, and this very small cross section with a new hacksaw blade took me about half an hour to cut through. It was the most absurd thing. It might not have been from this sample. It was from one of the aluminium samples, actually. I think it might have been from the fracture. But either way, it was from one of the Hutchison affected aluminium samples. And the interesting thing was, in the nickel that was on there and the zinc that you saw in the previous slide, this sample had in the 61, nickel 61, the fermionic isotope of nickel. All the others bosonic nuclei. It had 3.7 times the natural ratio of nickel 61. So that was a little bit shocking, and this was verified in a corona discharge, and I believe a corona discharge will create coherent matter, by Irina Savatamova, which she presented at ICCF 23. So we have corona discharge, which we know creates tritium, which we know does transmutation, which I believe definitely and 100% certainly produces exotic vacuum objects. This is producing the same synthesis of an element in the same increased ratio, but not necessarily the same proportion. But her experiment is a different one to a Hutchison effect experiment. But the fermionic isotope came out at a higher level. And I believe that this is because when nickel 61 is created, it can't live within the bosonic cluster of the overall structure, and it gets spat out more readily than the other ones. That's a hypothesis for you. But anyway, the point was, I was talking to Anatoly Klimov about this, and he said something quite striking, which we're going to come on to later. But I was saying about, I was seeing this this change in isotopic ratio in this Hutchison effect sample. He said, well, and it was kind of like, well, I want to share with something with you that we have found. And he spoke about he had some gadolinium that he had treated, and he put that in the same octopole mass spectrometer from Synthestech, and he came back and says, well, we've had an isotope completely disappear. Completely disappear. Okay, I'm going to come on to what that is later, but I want to go through his last presentation and some key points from that. But essentially, he described in this presentation a whole bunch of experiments where he saw COP up to around about 2. And I took the opportunity, because he had mentioned some things in there, for the first time, he mentioned the use of indium. Now, you might be aware that I used indium because it's mostly a beta isotope, and that if it was going to be able to... oh dear, now Windows is wanting to update. Sorry, I'm just really annoyed with Windows. It's a terrible thing. Okay, all right, let's hope that doesn't do anything. Okay, so... where were we in my story? In indium, yes. So I obviously used indium in the experiments with Amasa gas, and we used it in the Amasa vibrator plates, and we saw transmutation. We effectively didn't know, but we ended up replicating in the Amasa gas on the indium the observations of Matsumoto, where he used lead and produced carbon and other elements coming out of these lead balls, and we even produced the same kind of structures of these eruptions coming out. But of course he was using a lead wire into potassium hydroxide and light water, and effectively he was creating HHO on the fly and then consuming the HHO on the fly. So he was doing it in one step process, whereas we were producing the HHO and then creating the coherent matter, and it was creating these structures that then erupted and within a spherical volume cavity. It's like the magma chamber in a volcano, and then it was erupting the silicon and the carbon and so forth from that. So I chose indium because also it is the lowest melting point element that's still a solid, kind of like at room temperature, which doesn't easily get affected by, you know, reacting with water, and so it was just above a hypothesized temperature of what the gas from an HHO flame would be, and so I wanted to see the interaction of that. And in fact, I think it's 156 degrees, 0.6 degrees, something like that. And there've been various temperatures around about 125 to 135 or whatever for the HHO gas, and so it shouldn't melt it. Was my theory, and in fact, if you recall, it turned it to a rubber sheet, and then it glowed as bright as the sun, making the camera change its iris size so that the entire rest of the room became nearly pitch black. And so it was a phenomenal demonstration. Most people that had ever done HHO had looked to try and see what the highest temperature material was they could interact with and what it would do with that. Would it so-called vaporize it? I wanted to take the lowest temperature metal, but specifically I was also interested in the fact that it was indium and it is mostly a beta isotope, and could this inverse beta reaction of Parkhomov take place and so forth. But there was another reason, and in all of the experiments, based on my conversation with Anatoly Klimov, that he had given data at conferences subsequent to my meeting with him in 2018, he hadn't mentioned indium, and this is another one of these elements. And so I'm gonna show you this next clip here, which is from the presentation, and hopefully the audio will come through. You'll have to let me know if it does. Okay. All right.
Индия используешь, что при этом что с мутациями получается?
Нет, значит, у вас идея. Is the concept from the different materials like lithium, very large across such
People are hearing double sound, are they? So I think probably I'll replay that. I'll replay that and I'll kill the other sound source here, and we'll see if that works. Let me know if this works. It's just a short clip, and it's very, very important. This could be a seriously huge key to this space. So just let me know if this is working, this second one.
Индия используешь, что при этом с трансмутациями получается?
Нет, значит, возможно, concerning to the indium.
So why did you choose indium?
Indium, it's very important questions because of we use in our experiments the insertion in the cathode nickel from the nickels from the different materials like as lithium, indium, gadolinium, and others. namely these substances have a very large cross section with thermal neutrons.
Yes, you told me this in Sochi 2018, and I've been wanting you to make it public for a long time. So thank you for making it public yourself this time. So I already knew the answer. I wanted you to say it. So okay. Now, you have no idea how much I've wanted to say this for a very, very long time. Okay. Anyway, so there we have it. It is this. He used it because it has this high thermal neutron cross section. But I already showed you that the experiment produces, or his reactor that he uses this in, produces what they call fake neutrons, and these are these neutral clusters that come out, which are either the string vortex solitons or the exotic vacuum objects that are in the neutral state. Okay, so how this went down was, he told me about this gadolinium. Okay, and I'll look at the data in a second, and we'll just run over it. But he told me about this gadolinium 152. And gadolinium 152 is 0.2% of gadolinium. Now, the octopole mass spectrometer is so good, it will absolutely be able to see that 0.2% of a particular element isotope in a particular element. No problem with that. It saw in the control sample, it saw the 0.2%. In the processed sample, zero, nada, nothing. And I said to myself, oh my God, that will be, that, my friends, I thought to myself, that is going to be the unstable isotope of gadolinium. That is going to be the unstable isotope of gadolinium. Okay. The other thing I thought of is, my God, gadolinium is a neutron moderator. It's a neutron moderator. So we have lithium, a neutron moderator. We have boron, a neutron moderator. You've got things like cadmium, the indium, and you have this gadolinium, which has this incredible cross section. Okay, so it occurred to me that essentially my gut feeling way back when, that the things that were able to interact with neutrons, and this brings into question what actually is a neutron. Okay. But things that can interact with neutrons, because a neutron has an antineutrino in it, okay? And what is an antineutrino? Is an antineutrino a cluster of microneutrinos, like that way down? Is it just one of these donuts that's able to capture this material? I don't know. It's just some things to think about. But anyway, it's able to interact with whatever's coming out of these reactors and do something with it. And as I've argued before, if there's something that's unstable, that is the thing that will fail first. Okay, and in this case, let's have a look at gadolinium 152. So let me just bring up our wonderful Philip Power reaction table here. The other advantage with talking about this is that I can talk about this in my poster presentation next week, whether I get to America or not. Okay, so give me a second here and I will bring up a thing and we will go and have a look at our okay. So any questions? I will have a look in a sec. So one of the features of Nanosoft that I asked Philip to incorporate, just for the sake of it making it easy to work with, is the show element data here. And if you click on that, you can see here, maybe I'll zoom in a bit so it's easier for you to see. You can go in here and you can choose the elements in the periodic table, and we'll go down to 64, is it? 64, gadolinium, there you go. and you can see the element isotopes here. And gadolinium 152 here, 152 is the lightest of the element isotopes. And the interesting thing is that it is the only one that is unstable, and it's an alpha decay. It's 0.2% in the crust naturally. So of all of the element isotopes in gadolinium, the one that completely disappeared was this 152. Now, actually, if you go to something like tungsten and look at that, there is one element isotope which is around about the same proportion here, 0.14, but it is also an alpha emitter. Okay, so you can imagine that if you had a material that has one element isotope in it that will readily fall apart with not very excited clusters, because it's already unstable, then if that is evenly distributed, as one might imagine it would be, throughout the whole bulk of the material, and they're all blowing up practically instantaneously and producing 2.5 million electron volts, you can imagine that your tungsten would fall apart. Yes? It would fall apart. Okay, so is that what's going on when we have our tungsten disappearing? Let's go to indium here. Where are we? Indium. Okay. Indium is beta isotope, and that is 96% nearly of all indium. So that can almost entirely be caught up in this mess. And is that why it falls apart so very readily? I don't know. But that was kind of one of the things that I was holding in my mind when I was suggesting and using indium in experiments. And in fact, a long time ago, ready for the supernova experiments, which we will get to when I bought some silver and finalized my strange radiation shield, is I actually bought this extremely long time ago to put in the reactor. And this is boron oxide. This is B2O3 here, a container. And I was going to add that to our reactor and see what we had out of that. Okay, of course, it might just produce a lot more carbon, but there we go. Okay, so those are the things. Now, if we go in here and we look at neutron moderators, here, neutron moderators. What have we got? Has it got a selection of them down here? Okay, what have we got? Ooh, look what we have here. Graphite. Interesting. And also, if you could see it, did you not see any of that? Graphite. Graphite is a nuclear moderator. Why is that important? Okay, we'll look at nuclear cross-section here. It's not got a lot on there. Cross-section. We got anything here? Have you any use? I'm just trying to get sources which you can readily see. Now, in my presentation, in my presentation, I've got some links to some really good data. Now, I actually produced a chart of what different elements are very good at different energies and resonances, but I couldn't find it. I actually produced it for a presentation that I wanted to produce way back in 2018, 2019, but I just couldn't get to a point of having Anatoly admit this, and I couldn't just run with it on the basis of my theory alone. Okay, so what is the really, really important thing here? The really, really important thing here is that he didn't just tell me that the material that was good as a thermal neutron high cross-section material, it wasn't just that it was that. He was saying that what he has is he has his cathode, and it's emitting material, and then he has his anode, which is made of nickel, and the nickel anode has a chamber in it, and into that chamber he has lithium or boron or what do you call it, indium or cadmium or gadolinium. And in fact, when it's lithium, he actually rotates it vertically because the lithium becomes liquid, and so on. So he has that as a target. And he says without the target, he never gets really excess above a COP of 2. So no more excess than 100%. Okay? There's some reactors that in his presentation where I think he's getting 3.6. When he puts those elements in, and only when he put those elements in, does he get a COP up to around about 10. Only when there is one of these elements in his exotic vacuum object ball lightning plasmoid receiver anode does he get these excess heat in the order of about 10. Okay. Ken Shoulders said that you have this thing and it comes in, and the impact of the material, of the protons that are captured, or the oxygen or the cluster or whatever, when it hits the material, there's enough energy there to create nuclear reactions. And you can imagine that that would be the case, and that's kind of the principle behind P and Telly, except P and Telly, in my view, is the clusters are built and then they blow up, or they eject protons, and the protons are ejected and they hit into the lithium or they hit into the boron. In this case, you've got a whole plasmoid with whatever it is colliding into this material, and it's producing this excess heat. So why is that interesting? Well, there's other instances where we have data which cross-correlates to this, and so this is the first section. I'm going to do one more video clip from him here.
Индии используешь, и что при этом с трансмутациями получается?
Нет, значит, once more, concerning to the indium.
So why did you choose indium?
Indium, it's very important questions.
Oh, sorry. This is the same one.
Use in our...
Okay. Let me just check where I am in my own presentation here. Okay, all right, so... All right, I have some more points to make on the gadolinium. So at the Condensed Matter Nuclear Science Conference in 2021 in Assisi in Italy last year, if you recall, where I gave my coherent matter wave presentations, the organizer, Bill Collis, he actually runs the CMNS group and organizes all these conferences. I was sitting down with him one morning over coffee, and he was talking about the fact that Francesco Piantelli had basically stopped doing cold fusion or LENR research, and that he had shut down his lab, and the parts of the lab had gone to the winds. And he was invited in and asked, did he want to take anything? And he said he was very generous, and he gave me all these different various bits and pieces. He said, but the most curious thing was, and there was no explanation for it, he had a large sheet of pure gadolinium metal. And I thought, I think I know why he was using that. Now, of course, we know that in some states the clusters are magnetic. Would it be something to do with that? Obviously, the gadolinium is a known neutron moderator, and he had neutrons emitted, or what he thought were neutrons. Certainly, they activated gold, so they probably were real neutrons. And we've talked about how these protons interacted with the vanadium-50, producing a chromium-50 and a neutron, and that we had seen similar experiments with Me-356 and with Suhas-Ralkar signs of. And so Piantelli had a large sheet of gadolinium in his lab. But anyway, let's talk about the neutron cross-section data, which I have here. And I'm going to pull up some of this data, and there it is. You can go and look at these slides. But here's the cross-section for gadolinium 152, 152 F3, and 152 F2. So I'm just going to pull up these, and we'll see what they look like. Okay. So, two sets of data. This is the International Nuclear Data Committee from the International Atomic Energy Agency, and I think the head of the International Atomic Energy Agency is going to be at ICCF 24. It'd be a great shame if I can't have these kind of conversations with him. But anyway, here is this gadolinium 152, and here are the resonance peaks, and you can see it's around these energies of 10 EVs through to 1,000, 2,000, 3,000 EVs. But you can see here the Barnes here is very, very high, up to 10,000 in various resonances. Here's some other data around depending on the neutron energy and you know, whether it's a knockout reaction, but anyway, depending on the neutron energy, what reaction occurs, okay? And then here is the sort of a little bit more bar chart like data. Anyway, if you go in here, it has all your various elements that have a good neutron cross section, and it shows all the different sources and so forth. So where are we? What have we got here? Let me just oh no, I can't do it on here. Okay. What are we looking at here? I don't even know what element we're looking at here. Thermal photons. Thermal neutrons, rather. Okay, so you can look at this in the own time. Anyway, what I did with okay, you can see most elements don't have much going on. But when you do have a resonance, I don't know, this is boron 11, so here you can see the interaction here with boron 11. You can see there's nothing with boron 10. Is that right? Or boron 11? It's boron 10 that's the neutron. Anyway, these are the resonances here. This is carbon 13, carbon 12, carbon 14 here, and so forth. I actually did a composite chart, as I said earlier, where I took the principal moderation elements and plotted them and showed what would be a good combination of elements to use as a thermal converter. But actually, I don't believe it's just doing thermal conversion. What you've got with the gadolinium, it's near perfect. In fact, if the whole material could be gadolinium, that would be great. But you've got the magnetic block. We know a magnet will capture these things, or a magnetic material will capture these, like the iron 57 of Roitskev. Okay, so it doesn't. Nickel will do it, and so forth. So a magnetic material will catch them. Obviously, gadolinium is wonderfully ferromagnetic, incredibly. Okay, but it's also a neutron moderator. So, and with the highest, except for one, I think radioactive xenon isotope. I don't know. There are some, I think one thing that's got higher, but it's just fantastic with both of these aspects, which are key. I think it's cobalt. Yeah. So there's samarium cobalt. I think that's a good, because it's magnetic and so forth. But anyway, the point being is, if you have a thing that can moderate, whether that's lithium, carbon, boron, indium, cadmium, gadolinium, these things are potentially very good at interacting. Now, cadmium's not very nice because it's toxic. Indium I chose because it's non-toxic and it also has this beta isotope thing going on. Gadolinium's a lot more expensive. Lithium has its own risks with working with it. And boron, well, I got some boron. So I chose boron and indium as my preferred elements to work with. Okay, so what else do we have in my presentation? Okay, so the other thing was, which it speaks to many other experiments that we have observed this in. This is a translation from that same presentation. I couldn't find the clip to show you here today. But he said this. This is a hint. So we saw carbon in our reactor. So on a nickel reactor in Germany, I told you the whole reactor was covered with soot. So when we used helium as a working buffer gas along with water vapor, But when they replaced the helium with argon, there was no carbon. No carbon. So it means everything is clear that this is a derivative of light atoms, which can arise from water. Anyway, the point being is that when he gave it helium, which when you strip helium of its 2 electrons, you end up with an alpha particle. You ended up with triple alpha being synthesized, okay, in his system. When you replaced the working buffer gas from helium to argon, you didn't see any production of carbon in his experiment. Now, I'm arguing that you produce carbon directly if you get the charge cluster big enough, the ball lightning big enough, it will produce carbon. And obviously Matsumoto has observed this. Yul Brown observed this. Many people have observed this. This is another person to add to the tally who's observed large proportion of carbon. This is an experiment that can be conducted by Henk and by David Boutelier, seeing how much, because in their experiments they've often had the viewing window on their reactor fog over with carbonaceous deposits, okay, and obviously we've seen carbon on the brass electrodes in abundance, and even on the tips of these sort of Maxwell sort of structures, hexagonal type mesh like structures that are forms. You end up with something that looks like a diamond on the top of these carbon filamentary sort of structures that get produced. So I believe that we've produced in those experiments abundant carbon, and therefore this is another person to add to the pile. Now I actually question him here.
With the indium, it's impossible.
Okay, so the previous data where you...
Yes.
So can you show the data where you were observing carbon and you had a list of groups of elements, like the argon group, the light, where you had the light element discussion, just for the English audience?
Yeah. I repeat once more that the carbon is created intentionally, very strongly, when we use helium as a vacuum gas.
Okay, and you see conjugates of alpha, do you?
Yeah.
So there we go. So when he's using helium, he gets a large amount of carbon produced, and he also sees conjugates of and you can see, I think, even on the data on this slide here, you've got oxygen here, and so the carbon there is 9%. Okay, and so if you don't put anything in, you've got a reactor vessel that has no carbon, and you put helium, and you have a nickel electrodes, and you have a discharge with maybe hydrogen in there. Where's all the carbon coming from, right? So, seriously. Okay, and so abundant production of carbon. Okay, obviously if you've got water in there, you're going to have oxygen in there anyway. So the carbon is the interesting thing, this whole sooting process that we have seen happen. Okay, so then who on carbon? Well, this is something to think about. More on carbon I've got here. And why am I drawing your attention to this? Pure carbon as a moderator is used in RBMK reactors. These are the type of nuclear reactors that Chernobyl was. And they used these reactors because it was a quick way to make plutonium. Oh, sorry. Lost my slide now. And we know from the studies of Roitskev on the carbon moderator blocks from Chernobyl that uranium and other nuclear material was found within the graphite bricks. Okay, and so what this information from Roitskev, I think from 2006, tells you with 100% certainty that material was teleported into the center of the moderator blocks, which means which tells me something is doing that teleportation, and we know what that can be. That is our exotic vacuum object. We know from Shishkin's work that it can take ions and move them through metal and through air, and then deposit those ions on a photographic plate when it's being excited by the silver. And that's why the silver gets used in the shielding that was developed by and patented or patent applied for, but it's now invalid because it wasn't paid for and free to use by anyone. The use of silver excites these exotic vacuum objects. So if you can imagine you had a liquid metal cathode exotic vacuum object producing system, like the electrical particles of matter of the Tesla device from 1930s, or the exotic vacuum object launcher by Ken Shoulders from the 1980s, or some other system that maybe used a liquid metal like hot silver, or for instance gallium, okay, which doesn't need to be much above body temperature. If you used a liquid metal, in the case of both Tesla in the 1930s and Ken Shoulders, they used mercury in their case. You can imagine a situation where these produce these exotic vacuum objects, and the metal that's captured in there is transported. But if you wanted to protect your reactor, you would want to probably use graphite. Why? Because carbon, we know, interacts with this thing. I'm telling you, it is a pseudo-neutron moderator. It's a neutron moderator, and these act like neutrons, these neutral structures. And we've got other examples of this. In the analysis that found strange radiation in the early 2000s by Vysotsky of SV Stanislav Adamenko's Proton-21 reactor, they used metal dielectric semiconductor structure. And on the surface of that, they put some oil on there, which obviously contains carbon. So it's kind of something that it forces it disrupts the thing that is coming out and gets it to kind of like interact with the metal dielectric semiconductor under there. So this is a very, very good detector process here. And of course, we know that in Suhas Ralkar's reactor, which was claimed to produce a COP of 10, though we never was able to determine that, the Echo reactor, his fuel had carbon and lithium in it. Carbon and lithium. And I think probably one of the most beautiful arguments here is, and we showed this live on camera, is that HHO gas in the form of Brown's gas, to lower the temperature of the gas, they would add a hydrocarbon into it. Brown's would add a hydrocarbon into it. It wasn't lowering the temperature. It was changing it from being able to easily produce coherent matter to being disrupted from producing coherence and the production of thermal temperature rather than this non-thermal process of cutting material. And so we saw this with Amarza gas, where he put in a certain amount of methane or propane or even CO2. So that's got no hydrogen in it. It's just carbon and oxygen. And this increased the thermal temperature. But when we applied it to the same thin 1mm titanium sheet, it got a lot brighter. The bolometer read the correct temperature based on the color temperature and what you saw with your eyes, but the actual temperature was higher, but it could not burn a hole through it. It could not burn a hole through. In my view, it could not coherently eat through that material using coherent matter. Okay, so if you had a liquid metal reactor and you didn't want it to fail readily, your easiest and cheapest choice would be to line it with graphite. That would be your choice if you were using exotic vacuum objects in your technology. Graphite would be a choice, and also I've argued this before, boron nitride. Why? Because it's not only is it covalent rather than ionic. Ionic materials in the face of a high electric potential will and temperature will become conductors, whereas the boron nitride isn't so easily in. But in addition, it has boron in it, and the boron is a moderator. So if you were to create, like was done by Tesla, or like was done by Ken Shoulders, a high DIDT discharge liquid metal reactor, and you wanted to produce more heat with it and have it not eat itself to death, you would line it with graphite. So what I'm giving you here is the logic, the reason, the scientific basis, the history over the last 10 years of how I came to think that thermal neutrons moderating materials could be extremely important, and would explain our 2012 December the 14th experiment, first experiment where we saw excess heat, that unfortunately got me hooked on this. If it wasn't for that, I wouldn't be here. So thank you, Francesco Celani, and for your courage for sharing that experimental detail with us. And if it wasn't for seeing Piantelli and these other steps in the process, the reactor tube of the boron nitride reactor tube, and considering that, getting to the point where I could question, I could just raise the subject with Anatoly Klimov. I think neutron moderators are causing excess heat, and I don't know why, because it's not neutrons that are coming out, and Anatoly specifically saying, and it's the only time it's been said as a block in my experience of any presentation I've seen of his, specifically saying we only get more than a COP of 2 when we introduce either lithium, cadmium, indium, gadolinium, or boron into our target area of our nickel anode. Okay, he only gets the COPs going up to that 10 level when he uses these materials. And I would lump carbon into that as well, because it is a well-known moderator. The Chicago pile, the first nuclear reactor that went critical, man-made, other than these natural ones that occur in Africa and stuff, the first one that went critical, that was produced with pure carbon. It needs to be really pure carbon, okay? And that is, I believe, what you would need to produce excess heat. So that is basically my gift for everyone before ICCF 24, is if people are interested in excess heat, they first need to create exotic vacuum objects, micro ball lightning, itonic clusters, plasmoids in old parlance, coherent matter as I would prefer to call them, and you need to have this impact with or get to a level of resonance. And if you then want to protect your reactor at the same time as creating excess heat, the data is in the end of the beginning presentation. We recorded as one long stream when we looked at Amasa gas. When you add carbon to the Amasa gas, which I believe is creating coherent matter, because it does the same thing that other coherent matter systems like the Matsumoto does, and so forth, with this cutting through material. You add carbon to it and it raises the thermal temperature. It's a different outcome from the process. Okay, so that's pretty much what I wanted to say there. Okay, so I'm going to have a look at your comments here and see if there's anything I can add to what you want to say. Right, Gordon Doherty, welcome. Hi Corky. So hi Space Case. So Windscale used graphite as neutron moderator. It needed to be washed regularly, otherwise the graphite overheated and caught fire, as happened at Windscale. Well, there we go. Soot question. Will EVOs explain no soot in the box chambers of Saqqara? Not sure what you mean there. I wish I did know that. I do know when ball lightning can go through various material, it leaves a soot trail behind it. Looking at the field format of these neutral particles, at least from an electrical engineering point of view, I want something that absorbs that energy, and carbon is perfect for that. Okay. Can you do sonocavitation in a hydrocarbon oil, get heat, boil water to steam? Actually, that is, I think, what, and I'm going to forget his name, Max Formichev-Zamilov is doing. And I suggested adding something in there as well. Hi, Scotty. Okay. You wish you had a better visual concept of Klimov's apparatus. I have got some good images I've shared over the years, and it's in some of the presentations. So maybe I can get those out, and maybe I will find them and add them into the remote view blog on this. Yes, David. David's saying that he has a nice glass 54mm outer diameter quartz tube, and so this should soot easily. So I think it would be great for you to do an experiment with how should we put this, with argon first, and then do an experiment with helium and see if you get sooting. So unstable elements boost observed energy releases. Yes, that is my hypothesis. And certainly the observation of the gadolinium 152 completely disappearing implies to me that that would be the case. And if you look at the tungsten 180, which is a similar kind of small fraction of 1% of the natural tungsten, but it produces something like a 2.5 million electron volt decay alpha particle. If that is evenly spaced through our tungsten, and we have a coherent matter structure coming in like it does on the copper. Now the copper that we showed, the 10mm ball lightning producing these interlinked 5 micron wide with holes in there that were of the order of about sort of 70 nanometers, with this material being churned around and not melted in between with these kind of orthogonal holes. If you could imagine that that is going through copper and it's kind of just taking it on board, when you're going into a material in the same way, like, I don't know, a Langmuir probe in a sapphire reactor, and you have the coherent matter coming in there and doing the same kind of interaction, as soon as it starts interacting, it produces these alpha particles, which are the core of helium, which are the food because they are bosons, and they're easily grabbed and made coherent because they'll be highly charged. So it's emitting these alpha particles at 2.5 MeV. There's a lot of energy going on. There's a lot of alpha particles becoming free. And so if that's an alpha, there must be some electrons around, because those 2 protons that are forming that alpha particle that's coming out have left behind 2 electrons. So there's 2 electrons as well that will feed the beast, and so that will churn through and consume that tungsten. And if it energizes it to another level, you could get the stable elements falling apart, not just the unstable, but the stable elements as well, as per the suggestion of the David Freiberger paper, where it's knocking the atom nuclei off its reference to the local Dirac sea, and then the nuclei fall apart, and so you get this 1 gigaelectron volt per nuclei. And so you're getting, I think if you're getting around about 6 million electron volts per nucleon in a deuterium fission to helium, what are you getting from 1 proton decaying is 1 gigaelectron volts. 1,000 million electron volts divided by 6 is like 15 times more energy than fusion. This is like really the end of the line in terms of getting energy out of matter. So yeah. Daniel, sure, you might say that, but I couldn't possibly comment. Yeah, sorry, I was actually, in fact, did I not add Parkhomov on there? I thought I had him in my slides at some point. I did talk about him earlier, but I missed that point, yes. In more recent Parkhomov presentations, he has shown that using lithium and boron produces the highest excess heat out of his experiment. So we have the same thing. So what are the elements? Any element that has a good thermal neutron cross-section, I would suggest lithium. And in fact, they want to produce tritium in the hot fusion reactor by having a neutron coming out and interacting with a lithium blanket and producing tritium. But anyway, lithium 6 is a good neutron moderator, but just lithium anyway. And then carbon, boron next, then carbon, then cobalt. Is it cobalt? Yeah, I think it's cobalt. Whatever's before indium. Let me look at my periodic table. I'm getting tired now. Oh dear. No, sorry, cadmium. Is it cadmium? Whatever's before indium, I think. Cadmium. Yeah. I think it's cadmium. Maybe not. Maybe it is. Oh dear. This is where I would have liked my chart that I got ready many moons ago. I just couldn't. My directory wasn't. Yeah, it's cadmium. It's here in the P table here. Cadmium, indium. So you've got lithium, boron, carbon, cadmium, indium, and all the way down here, gadolinium. Okay. Hi, Brian. So, Brian, what we've been talking about is methods, and I'll do a recap in a little while, to increase excess heat in systems that use exotic vacuum objects, string vortex solitons, micro ball lightning, and the like. Not cobalt, sorry. I mean cadmium. Sorry, I was getting my curse mixed up. So Gordon Doherty says nickel 61, that's the most stable element, is it not? Just ahead of iron. No, nickel 62 is the most stable element isotope. Okay, so I'm just going to run through this presentation quick for those that missed it, and just to do a recap. So this was from under 2 times to 10 times excess heat, leveraging the power of exotic vacuum objects. And we talked about that how in December the 14th, 2012, I gave my report of the MFMP's first successful Chilani wire replication, which occurred on 12 seconds past 12 minutes past 12 on the 12th of the 12th of the 12th, Californian time. It was started at that time with everyone watching. However, it actually was started in southern France in Mathieu Villat's lab. And I gave the presentation 2 days later in Rome in a military base. And after I gave my presentation, I went out of the room, and a very excited senior military individual tapped me on the shoulder from behind and asked me, or rather told me, you need to use an alkaline metal. And rushing through my head was the thought of Pons and Fleischmann using lithium deuteride in their experiments. And so I suggested lithium, and he didn't give anything other than something that suggested that I'd made the right guess. And so lithium was in my head, and we had previously tried to in Ryan Hunt's Hunt Utilities in Minnesota in USA replicate a duplicate of the reactor that Mathieu Villat had run we did this previously, but tried to leapfrog where Celani was, where he wanted to go, and use fused quartz, but it didn't produce any excess heat. So we made the mistake of not doing a proper replication, and when we did, we saw excess heat the first time we did a proper replication. And that got me thinking what was in the borosilicate glass, which was important. And there was boron and lithium carbonate. So we had lithium, boron, and carbon in that material. And so that was a data point for me. Now, the boron got a little bit more interesting a little later down the line when we visited Piantelli in 2015 January, thanks to those people that sponsored the work by of the Fedora project. And we had 7% of the Maycore that was the main part of the internal structures of that Piantelli Ficcardi reactor was made of boron trioxide, and this is why I bought some boron trioxide later to use in the supernova reactors. And then we found out that Barkamov, in one of his first high energy producing nickel hydrogen reactors, was using boron nitride. And around this time, the Piantelli patent was published, and it showed that he was saying protons were coming out, and his preferential secondary material for these protons to interact with was lithium, like the Cockcroft and Walton experiment from 1932, and boron, and these two are aneutronic reactions which would produce a large amount of heat. And I kind of recounted this level of thinking on the 3rd to 8th of June 2018 at ICCF 21 in Boulder, Colorado, to Celani, and he recalled the fact that he had this unexplained phenomenon of a Maycore support structure for his Celani wire. The internal of that Maycore structure had a tube running through it, and he had a thermocouple in there, and it got really hot, and he didn't understand why it was much hotter in the center of that, and so then he had an explanation. And then I talked about a subsequent to that meeting with Celani publication on lena.su of a video where on the 4th of July 2018 that was published, where in Anatoly Klimov's lab you have a lot of the usual suspects in the community in Russia, all discussing these pseudo-neutrons that are being emitted from the ball lightning, the plasmoids as he calls them, from his inflow plasma vortex reactor. And you've got a Tesla coil here, and this is where the water vapor and whatever is injected, and you have a cathode, and then down here you have an anode, and in the anode it has a secondary material. This is Anatoly Klimov himself, as he was on the 3rd of October 2018, and based on a conversation that came out of this data that came from analysis of Hutchison samples, he told me that, we have indium that has disappeared from our gallium-152 that has disappeared from his reactor. And I then came back the following day I'd had this epiphany overnight, and I thought, well, basically things that are able to interact with thermal neutrons are key to producing the excess heat from whatever is going on in these reactors. Something is coming out and it's interacting with neutron moderators, but it isn't neutrons, and it's producing this excess heat, and that was when he was like, it's one of these moments when you know the other person, you've basically worked it out, and the other person has to say what they already know, which was that they only got a COP of up to and around about 2, unless they used these thermal neutron moderator elements in the target, and that's when he got COPs of 10. And so that was that. And so my advice is for people that are wanting to produce excess heat using systems that are in the family of exotic vacuum objects, which until I see a fantastic amount of data spreading many decades, possibly 100 or more years, that paint a whole different universe, then this is what I think it is. We are using a natural phenomenon. It has behaviors, and if if you don't give it these thermal moderating materials, thermal neutron moderating materials, the exotic vacuum objects can just go through ordinary material and in some cases destroy it. And so if you want to be focusing on excess heat without your reactor being destroyed, you need to have graphite and I would suggest the use of boron nitride. And then outside of your heat producing reactor, and this is for those people that think they're using a different technology, you're not, in my view. You should be looking at the work of Shishkin for shielding the residual radiation that makes it through using this latex, silver, and something that is a phosphor. And we talked about zinc oxide as one of the choices of phosphor, but you can use some of these sort of lanthanide type phosphor base materials in there, and the patent is free to use. There's literally no excuse to protect your workers. There's literally no excuse to not protect your workers, and literally no excuse not to at least not take the risk of exposing people to cancer-causing particles. I think even if you don't disclose that you're going to be using this protection, it is patent-free, like I said, because of what's happened with Shishkin's patent. You should do this anyway and just not say it. Just pretend your technology is different and just use the protection anyway. Well, Blues Doctor, I would be interested to see how the scintillator comes out, but now we know how, from Shishkin's work, how the scintillators, the scintillation zones interact with the string vortex solitons. According to his theory, this produces these strange signals that was observed in 2011 at the original Rossi meeting, where Francesco Celani was 7 meters away from the reactor behind a closed door with 2 battery-operated sodium iodide scintillators, and just before he came out and said the reaction has started, both of the scintillators went full scale and stayed there for about 2 seconds. And this is what happens, and I've explained the whole process, where you get this hot degas nickel. You then put in the hydrogen. The nickel disassociates the hydrogen into atomic hydrogen. That has a magnetic moment that binds to the magnetic moment of the then cooled nickel, and then the nickel rises through its Curie temperature and instantaneously expels all of these magnetically bound adhered protons at exactly the same temperature, which is the requirement for producing the coherent matter waves. And this leads to the formation of the coherent matter clusters, and then they can sometimes stay stably, and sometimes they're unstable and they blow up and they emit these quanta of this coherent matter wave structures that are the strange radiation, and that in the form of string vortex solitons, according to Shishkin, but that is, as he says, the neutral form of exotic vacuum objects that can pass through matter. And this has almost zero attenuation, but when it comes into the sodium iodide thallium doped scintillator, it interacts with these the photosites and produces these spurious signals that he observed in 2011. And this is what Thermocore experienced this. We experienced it in 2013, which got the certain people very interested in what we were doing, because it's inevitable we would find out how this works. And that was in 2013 when we had the Celani wire, and it was we had a leaky cell on one side, and over a number of days it would go from its operating pressure that we were running at 3 bar down to atmospheric at 1 bar, and we would recharge it with hydrogen. That came out of Electrocan. It went in icy cold. It flash cooled the wire. The wire then almost immediately got hot again because it's electrically powered. That then absorbed the whole process went as I've just described it. The hydrogen is split it adheres, and then as it instantaneously goes through the Curie temperature, it then comes off and forms the coherent matter. And this is essentially what was going on in our GS 5.2 when we took it through the Curie point. We merged our understanding with what Piantelli said we should do. And Piantelli very, very specifically, absolutely very, very, very specifically said, we must do this process down between the Debye temperature and the dissociation, catalytic dissociation temperatures. And then we must get up as close as we possibly can to the Curie temperature, and then extremely fast go through it. And it took a long time for me to understand the hidden message, which was not described in there, where this would form the coherent matter. And so, that's basically the nub of it. So this is not patentable. It is open for people to use. The methods now, because unless there is a patent that specifically describes these materials, if you want to produce excess heat, this is not patentable. The use of liquid metals is not patentable. The use of electric high DIDT discharges is not patentable because of all of the work of Ken Shoulders, and the protection methods are not patentable. You just need competent people with the will and the support and the finance, and this can be delivered. It can be delivered, and we're talking about a COP of 10. Now, the problem that Klimov has had, it eats the reactors. He hasn't made that connection necessarily to having a containment. There's two types of containment. You can either contain the structure that is the exotic vacuum object structure, the ball lightning, okay, and then break it deliberately and have a containment that one thermalizes the broken structure, which would be, in my book, this graphite, and then probably boron nitride behind that. And then secondarily, you have the protection beyond that. So there's many ways to do this, and many embodiments that I believe would work. And you can build off the work of Solin, of HHO work. There's so many different ways to approach this. But I think certainly in what I've given in this presentation, with the support of the on-camera real-time presentation that we captured of Dr. Royston Amar's HHO, and the observations that were produced that match those of Matsumoto with his ball lightning itonic clusters. I think really it's got to be really clear to people. And I would love to be able to go to the conference. And what I'm going to do right now then is I'm going to, in the blog, I'm going to publish a link to a Zoom in the next 10-15 minutes, and people can join me, and I'll just talk through where I am with that, and also some other things which will not be on this live stream. So if people want to join me there, that would be great. So I'll just see if there's anything questions here. Silver and fluorescent phosphor powders held by latex. Yes, that's basically it, Stephen B. Halls. So, Space Case is saying, so shielding from the EVOs and the bagel coil field is identical, right? They are just different sizes. Maybe. So, my learning, when I was looking at back in 2017 at things from the Echo Fuel, where I saw the first strange radiation, and the most beautiful, what I call the lion's paw prints in Lion in late September 2017, those original paw tracks, where I derived the basic structure, the toroid with the sort of vortex structure going in, and this sort of pseudo monopole structure, where there's one yin, one yang. I kind of like I kind of wasn't at the point of understanding very certainly that this was a structure that doesn't necessarily depend on ordinary matter. Then when I saw the footprints on the Hutchison fracture sample, the outie and the innie and the quantization, where that let's say that was electric, it then joined together magnetically, and then that produced an electric, and that joined together electrically, and then that produced a magnetic, and so on. And that fractal structure that I published on February the 17th 2020, that was a point where I'm seeing the footprint of something which I don't see in any of these different examples, but I see a clear, repeatable structure. Okay, and so something is able to do that to material and leave no presence of itself behind. Okay, and so I thought actually I would never be able to see these physically in under a microscope. I thought it would always be this phantom, this ghost footprint. It's like the Sasquatch has walked across the aluminium and it's left big paw prints. You see it in the cupric oxide on the line. You see it in the aluminium and the fracture sample from 2007 from John Hutchison. So I couldn't. It was kind of like, am I ever going to see the real thing? But then Henk Uren's beautiful Vega Valley sample came into my possession, and on April the 22nd, there it was. I saw these things for the first time, and it was like, wow. And what you have to imagine is that these vacuum current structures, maybe at certain levels of intensity, can interact with matter, and they then ionize them, and then you get the ions wrapped up in this structure. So there's the exotic vacuum object structure, which doesn't necessarily have any solid material in it, right? And it can be neutral, it can be electrically charged, or it can be magnetically charged, right? So it can be neutral with no electric and magnetic charge, or it can be electrically charged or magnetically charged, depending on its clustering. And I've shown you how if you get, we've shown on the quartz from Lion that on a very tight 8mm, I think it is, internal diameter, I think it's 8mm or maybe 10mm here, right? On this one, we saw on the inside surface, you can see the one toroid here, but we had three of these come together in a classic sort of three-legged man, a trefoil, like you would see in a church, you know, where they're overlapping and you have the interference zones. You know that they are the same pole, and they were like three north poles joined together. And because of the angle that they're on there, we know that they can not only come together and they're like, but they come together, but they don't completely merge into one. Okay. That is 1/4 of a dodecahedron, which is similar to the structure that Moscow Nuclear Physics Institute saw. And so that is a sphere. And if they're all composed of norths or they're all composed of souths, then you are creating a true magnetic monopole that has a defined size. It is not a singularity. It is a defined size. Now, when I say monopole, it has beams coming out of a single pole and then areas which can interact with matter. Okay, so it can consume matter, and in one case it throws out stuff, and in the other case it keeps putting it in. So is one a white hole, is one a black hole? I don't know. These kind of things were observed by Matsumoto in the flesh, and we saw something similar on indium that was exposed to a Mars vibrator. So I don't know. But what I can say is I believe that these can be these pseudomagnetic monopoles, and then they can cluster into a state where they are effectively monopoles. And does that monopole then form the magnetic core of a ball lightning, and then around it you get other clusters? And so do you have a donut around a sphere, and is that whole thing able to repeat itself, if you know what I mean? It's self-similar on that kind of level of clustering. Because when you see, for instance, in the Ritzkev work, where he has the exploding foil, and we know that these structures, they can travel along wires because that was defined by Matsumoto earlier to the Ritzkev exploding foil work, then he has this ball lightning that appears above the reactor outside of the chamber where the water and the polymer and the aluminium was. It appears above the chamber, and then a few milliseconds later it splits up into micro ball lightning. So there is a self-similar structure of the bulk that can be formed. So is it the pure electromagnetic phantom that can be stopped by these? Maybe. So the shielding for EVOs may be effective at shielding the electromagnetic phantoms, and it's not because it's shielding it. It's because when it goes into the silver and photo fluorescent structure, the phosphor type materials, it's actually exciting it and disrupting it. And this is what Ken Scholder said, you know, interacting with certain types of material, the exotic vacuum objects can dishevel and fall apart. Now, is that disheveling when it's just a pure electromagnetic phantom? Well, probably, yeah. And so that would be great if it is. Ken Shoulders did say that one of the only things that can stop an exotic vacuum object projectile would be a exotic vacuum object skin, and you can understand why that would be. Hopefully, if you've been listening, I hope you would be able to understand that coherent matter, when anything comes into it, it's going to be consumed. It doesn't matter whether it's light or matter. It's going to, in even exotic vacuum objects, it's going to become part of the coherent matter structure. So, it could be just that pure electromagnetic structure, or a combination with electrons, or a combination with electrons and ions, or whatever else. Yeah, so we've used borax in our, as protection in our experiments, yes. Boron nitride, it could potentially be a solution for some of this pseudo-neutron flux coming out. But what we have to know is that you kind of need to excite these things by giving them free electrons. So Ken Shoulders described how if you don't feed in exotic vacuum objects, the charge goes down all the way to the fact that it doesn't express any charge, and then, in his words, it can walk right through things. I believe that silver, because it is the most conductive element, that means on the surface of any silver nanoparticle or silver particle, it has a huge amount of free electrons on the surface. And so when the exotic vacuum object neutral comes to interact with it, it grabs a load of electrons and becomes a charged structure, which then means it starts to interact with other charged structure like ordinary matter. And then that means it can start to dishevel. So I think that's the step-by-step process. Silver is chosen, in my view, because there is no other choice. It is the static material that is able to most readily provide free electrons to the incoming neutral cluster. Okay, so therefore silver is the choice. So borax might be able to create a bit of heat from it, but will it stop them? Maybe not. I think you need to use silver. So you might think that actually silver impregnated carbon, or silver impregnated lithium, or silver impregnated gadolinium might be the most favorable types of materials. You could use indium as well. So a mixture between silver and indium might produce. Anyway, what I've said today will make any variation that a person ordinarily skilled in the art might want to produce as a patent invalid because of what I've said today. And that is the purpose of what I'm doing today. It's to make these concepts invalid for anyone to profit from. But we need the energy. We clearly need the energy. So let's try and work together to deliver the technology, okay? It's kind of like it's walking like a duck. It's quacking like a duck. It's got wings and it floats on water and it tastes like a duck when you cook it. So it's probably a duck, okay? Okay, so I'm going to say thank you, and I'm going to post a link in the next 10 minutes, and if people want to join me on a live Zoom call, you're welcome to do that. So I'm going to say thank you very much for your time. It's been good to be back with you, and I will see you soon. Sayonara, dobro noc, buenas noches, buenas sera. Good night.